Welcome back, everyone. This is the last session of the discussion meeting. We have two short talks to begin with, followed by two 1 hour lectures. Our first speaker is Siva Heramb, who is a PhD student at the Indian Institute of Technology, Delhi, in India. He's going to talk to us about the effect of stratification on near inertial waves propagating on a beta plane. Siva, please go ahead.
Thank you, Mani. Hi, everyone. I'll be talking about the effect of stratification on near-inertial waves propagating on beta plane. Firstly, I would like to thank the organizers for this opportunity to present my work. A short introduction about near-inertial waves. They are internal gravity waves at the local Coriolis frequency f, and which propagate in a stratified medium. And they are generated basically due to the variability in wind stress, either in the stress magnitude or direction. Brief literature. So the review paper by Alford gives a comprehensive picture where the horizontal wavelengths are mentioned to be about order of 100 kilometer, and the vertical wavelengths vary from 100 to 400 meter, and they're known to strongly contribute to shear in the upper ocean. Eric showed that the variation of the Coriolis frequency with meridional direction imposes a time-dependent length scale on the waves and an upper limit of 1 to 2 weeks for the mixed layer energy decay. Moelis and Smith calculated the radiation of inertial energy into the interior in the linear regime and obtained expressions for the evolution of mixed layer energy. Johnston et al. Made some observations in the Bay of Bengal, and they proposed two decay mechanisms for the near inertial waves, namely downward radiation and shear driven mixing. On the right, we see a picture of the tropical cyclone genesis and tracks from the past 4 to 5 decades in the Bay of Bengal. So we see that there is intense storm activity in the Bay of Bengal, and near inertial waves are generated and also confirmed from the observations. As Eric told yesterday, that these internal wave spectrum has peaks dominated by shear in near inertial waves for peak in the energy and shear. So potentially they're important components in upper ocean and deep ocean mixing. However, the propagation and decay remains unclear, and the parameterizations are not accurate in the global models. So our motivation is to study the effect of stratification on the mixed layer energy decay, the shear, and any nonlinear effects present. So this is the computational framework. We performed simulations in regional ocean modeling software ROMs. We have a 3D box of with meridional domain of 1000 kilometer denoted by Y, and zonal direction X, and the vertical depth of 2 kilometer. The stratification profile is basically we have a mixed layer at the top, 30 meter, and linearly increasing density below the mixed layer. So the N is constant. We impose initial velocity of Gaussian profile of width 500 kilometer in the mixed layer, and we see how this evolves due to the beta effect and how the near inertial waves are formed or the inertial waves are formed below the mixed layer in the stratified medium. So the conditions are in the lateral direction, the bottom drag at the bottom of the ocean. So here I will show a video of the meridional velocity in the depth and in the meridional direction, that is the YZ plane, for the case of stratification value of 0.0049 below the mixed layer. So initially the meridional velocity is 0 everywhere, and as time progresses, we see that near inertial waves are formed below the mixed layer, that is 30 meter here, and they propagate downward and southward. We also see that the beta effect imposes a meridional wavelength decay factor of beta inverse as reported by Eric. Yeah. Here I show the vertical velocity contours on YZ plane, and for 4 different cases of stratification increasing from A to D. We see that as the stratification increases, the waves become shallower, meaning that the phase velocity angle made with the horizontal is increasing. And importantly, we see that as the stratification increases, the vertical length scale of the waves at a particular time observed is reducing, which could mean that there are presence of higher modes when the stratification is higher. So we performed proper orthogonal decomposition, which is a data-driven technique to basically obtain coherent structures from the data set. Here we are interested in the vertical velocity profile, depth profiles. And the POD would give different shapes that contribute to the actual velocity, vertical velocity, based on the energy. It sorts based on the energy. So for the case of N0, where the stratification is constant, we see only one POD mode with 100% energy, almost 100% energy. And as the stratification increases, we see that the mode 1, POD mode 1, for the case of N1 has a typical shape of normal mode 1. And for the case of N2, we see that the POD mode's first mode's energy is reducing, and the vertical length scale is also reducing as we go further to N5. And we see that higher and higher POD modes are required to contribute to the total energy of the vertical velocity profile considered. Here I show the FFT spectrum of the vertical velocity at latitude of 250 kilometer, or the y equal to 250 kilometer, and a depth of 80 meter for 3 cases of stratification. For the case of N0, we only see a inertial peak because there are no, it's just like an inertial oscillation, I would say. But as the stratification increases, we see that a 2F naught peak is formed. And with further increase in stratification, the 2F naught peaks dominate the frequency spectrum. So these 2F naught peaks could be due to the nonlinear interactions among different modes of inertial waves, as reported by Dheeraj Verma. So coming to the volume average mixed layer horizontal kinetic energy, normalized, here we plot it with the normalized value from using the initial value of HKE. And we see that as the stratification increases, the decay of mixed layer inertial energy is faster. And the 50% energy decay time for a case with 0.0049 per second is about 20 days. And primarily we see that the HKE decay is due to the outgoing energy flux from the base of the mixed layer. And we see that the dissipation is not contributing much. And the decay is primarily due to the outgoing energy wave flux, as can be seen from the normalized values here. We considered a step-like stratification to mimic the presence of a pycnocline, and where we have initial mixed layer, below which we have a pycnocline region with constant n of values shown here, typical of the Bay of Bengal values, and below which we have a constant stratification of 0.0049. So the similar trend is followed, where when the pycnocline strength is increasing, the mixed layer energy decay is faster. And for a case with 0.02 per second n value in the pycnocline region, the 50% energy decay is about a week. So here I show the vertical velocity depth profiles in the top 250 meter for the cases with the pycnocline N6, N7, N8. We see that as the pycnocline strength increases, the vertical length scale in this region of 250 meter, top 250 meter reduces, which could mean that there could be higher shear for the case with stronger stratification. So we quantify the vertical shear, And we see that as the stratification increases, the region of strong shear zone is increasing, particularly with presence of a pycnocline. For the case C and 6, the magnitude is quite large for the shear compared to the lower stratification cases. And the Richardson number, here we show the Richardson number, gradient Richardson number falling, the region where it falls below 1. Unlike the increase in shear with increase in stratification, for the case of Richardson number, the region where the instabilities can be present is reduced, because probably due to the stabilizing effect of the strong stratification. But overall, we see that there is strong shear below the mixed layer, and the Richardson number falling below 1 is interesting and could lead to changes in the mixed layer depth or mixing at the base of the mixed layer. So the initial velocities which we have given in the previous simulations were for the case with 0.1 meter per second at the center line of the Gaussian profile. And for these cases, the HKE decay rate matches well with the Moelis and Smith solution, theoretical solution. And for the case, as this initial velocity increases, we see that the HK decay rate is faster, and it deviates from the theoretical solution, and it takes about 14 days for 50% energy decay, in contrast to 20 days for the case with 0.1 meter per second, which is about a 30% decay, and it's significant. The FFT spectrum for the case with U0 0.3 meter per second at 9 different locations in the domain is shown here. We see that a dominant 2F frequency is dominant overall, and signatures of 3F and 4F are seen in the northern side of the domain, which is interesting. So, so the viscosity we have considered previously is a constant radial viscosity model, and the value is 10⁻⁶ meter square per second. And the figure shows HKE decay rate for n equal to 0.0049 and U0 0.1 for all the cases. For the case with 10⁻⁶ eddy viscosity, the 50% energy decay is happening in about 19 days. But as the eddy viscosity is increased to 10⁻⁴ in the case of CeV4, it has significant impact on the HKE decay rate, and the KPP model has about 5 days, which is significantly different from the case we considered CeV6. So for a realistic value of 0.02 per second for the case of N8 here, the 50% energy decay we saw for the case with CeV6 or the 10⁻⁶ eddy viscosity is about 7 days. But considering the realistic values of about 10⁻⁴ or 10⁻⁵ eddy viscosity in the ocean, this could be less than a week, even in the regime of evolution in a beta plane. Summarizing, the beta effect reduces the meridional length scale, and near-inertial waves are pumped into the stratified interior. Large N would indicate smaller length scales and faster decay of mixed layer kinetic energy. In fact, we see that the decay rate is proportional to n power minus 0.63, and a prominent 2F frequency is seen. With higher velocities, there is faster decay of HKE compared to the theoretical estimate, and presence of 3F0 and 4F0 superharmonic waves. And there is region of strong shear and Richardson number falling below 1. And this region is larger when the initial velocity is larger, indicating shear instabilities and requiring further investigation for the effects of nonlinearities in the decay of mixed layer energy. So some ideas we have for future work are high resolution simulations to understand the shear driven mixing, particularly the TK budget, the spectrum, and momentum and heat fluxes. And importantly, will the mixed layer depend due to these strong shear and Richardson number falling below 1 at the base of the mixed layer? And what effects the nonlinearities have on energy decay? Another avenue is understanding near inertial wave driven mixing using observational data. Can we predict the near inertial shear or eddy viscosity or diffusivity using the observations of data from wind stress, currents, and stratification? And will these help in improving in the global models, the parameterization of NAWs in global models? Owing to strong mesoscale activity in the Bay of Bengal, another avenue is interaction of these near inertial waves with mesoscale features like fronts. That's it. Thank you. Thank you for the opportunity.
Thank you, Siva. That was perfect. Are there any questions for Siva from the audience? You could either type in the chat box or unmute and speak, whichever way you prefer. So, Siva, there's a question from Jitendra. Did you check if increase in total depth of water column influences? Yeah, I guess influences your overall the propagation of near inertial waves energy.
So we haven't looked at that, but Gill's paper from 1984, I think, looks at that, and they say that the total depth of the water column will not, I mean, will only affect the averaged mixed layer energy decay, but the overall energy decay is almost the similar. I mean, the averaged picture would be almost the similar, leaving out some minor details. I mean, it wouldn't affect much.
Just for clarification, what was the depth you had taken in your simulations?
I have taken 2 kilometer, 2000 meter.
Thank you. Are there any other questions for Siva? So I had a question, Siva. You had your case of n naught equals 0. What exactly is the stratification you are considering? N naught 0 means you have a homogeneous layer at the bottom, and
we have a constant density. I mean, ocean or the domain. Yeah.
So it's just a constant density throughout the entire depth, is it?
Yes. Yes. Yes.
Okay. So that's like a 2 kilometer slab.
Yes. Yes.
Okay.
The pumping of inertial waves. Sorry. Yeah.
Okay. Then why do we get a vertical profile in such a scenario?
The vertical profile is basically it looks like something like this. So it's just, I guess, they are like inertial oscillations which propagate towards the left. They cannot be called inertial waves as there's no stratification as such.
Okay. Okay. Thank you. There is a question from Robin Roland. He asks, the pumping of near inertial waves can occur in other conditions too?
Sorry,
if the pumping of near inertial waves can occur in other conditions.
I'm not very clear what other conditions means. Is it in presence of some other eddies or?
So I guess he's asking. Yeah, you mentioned near inertial waves being generated by changes in wind stress. My interpretation is, are there other conditions where near inertial waves could be generated?
Okay.
Not only because of the beta effect. Okay, so he's asking, you mentioned the beta effect. Are there other mechanisms by which near inertial waves could, I guess, propagate downwards into the deeper ocean?
So in presence of mesoscale eddies, these near inertial waves are believed to get trapped in anticyclonic eddies and they propagate downward. In terms of generation, I guess I'm not sure, but maybe I have in my back of my mind, I have some recollecting some papers where they mentioned that at fronts there could be like formation of inertial waves or inertial waves forming from turbulence, but I'm not sure. I cannot surely say that.
Okay. Thank you, Siva. Okay. So if there are any more questions for Siva, I am sure you can directly contact him or ask him during the break. Thanks, Siva. We will move on to the next talk by Srilekha.